In a distant solar system, a giant planet is orbiting its star at a distance that should have meant certain death. The star, a quiet remnant now, was once a raging red giant that should have expanded and swallowed the planet whole. And yet, the planet is still there. Astronomers are now faced with a paradox, a world that survived a death sentence that our models of the cosmos say is absolute. The system is located 250 parsecs away in the constellation Ursa Minor. The star is named Baekdu, and its impossible companion is Halla. Halla is a gas giant, similar in size to Jupiter, but its orbit is shockingly close, circling Baekdu at a distance of just half an astronomical unit. For context, an astronomical unit, or AU, is the distance from the Earth to our Sun. An orbit of 0.5 AU places Halla well inside the path of where Venus would be in our own solar system, and not much farther out than Mercury. This is the stellar danger zone. Standard models of stellar evolution are clear on what happens next. A star like Baekdu, as it runs out of hydrogen fuel in its core, is destined to swell into a red giant, an event that has already happened. When a star like Baekdu becomes a red giant, its outer layers expand enormously. Our own sun, during its red giant phase, is expected to swell to a radius of about 1 AU, engulfing and destroying Mercury, Venus, and possibly Earth. Baekdu's red giant phase should have pushed its stellar surface out to approximately 1.5 AU, far beyond Halla's current orbit. The planet should have been vaporized. The planet's existence was first confirmed through years of patient observation using the radial velocity method. This technique measures the tiny, rhythmic gravitational tug a planet exerts on its star, causing the star to wobble. The data was unambiguous. A Jupiter-mass planet was orbiting Baekdu in a tight 93-day period. The observation itself is not in doubt. The planet is there. This immediately raises a question for astronomers. Could we be wrong about the star? Perhaps Baekdu isn't a post-red giant star at all. Maybe it's a different type of star, one that only looks similar, and the red giant phase is still in its future. If that were true, the paradox would dissolve. Halla would simply be a planet with a dramatic, but not yet fatal, future. However, subsequent observations confirmed Baekdu's identity. It is a red clump giant, a star that has gone through the red giant phase, survived a helium flash in its core, and has now settled into a new, stable phase of burning helium. This is not a star preparing to swell. This is a star that has already done so and shrunk back down. The planet, by all rights, should be gone. So we are left with an impossible fact. A planet orbiting inside its star's former death zone. This isn't about a future event. It's about a world that appears to have survived a past apocalypse. To understand why this is such a profound challenge to astrophysics, we need to examine the standard life cycle of a star in more detail and see just how violent that red giant phase really is. Building on our earlier discussion, let's precisely define the death zone around a star like Baekdu, a region that Halla inexplicably survived. The standard model for sun-like stellar evolution is clear, derived from decades of observations and complex computer simulations. It outlines a predictable, yet incredibly violent transformation. When a star exhausts the hydrogen fuel in its core, nuclear fusion ceases there. However, fusion reignites in a shell surrounding the inert helium core, causing the star's outer layers to cool and expand dramatically. This expansion is not gradual, but rather a profound change in the star's entire structure. A star like our Sun, for instance, is predicted to swell to an immense red giant, expanding up to 100 to 200 times its original radius. This means its surface would extend roughly to Earth's current orbit, engulfing Mercury and Venus in the process. The sheer scale of this expansion creates a vast region of destruction. This expanding envelope defines the star's death zone, a region where any planet caught within would face certain annihilation.
Planets don't just vaporize instantly. They experience immense drag and friction as they plunge through the star's thickening, super-hot atmosphere. This interaction causes their orbits to rapidly decay. Over a relatively short astronomical timescale, often just thousands of years, the planet spirals inward, closer and closer to the star's core. Eventually, it succumbs to the intense heat and tidal forces, being torn apart and vaporized completely. This is the predicted final outcome for any world in the red giant's path. This understanding is not speculative. It's a cornerstone of astrophysics, confirmed by observing thousands of stars at various life stages within star clusters. Stellar models consistently predict this dramatic expansion, and we see the spectroscopic signatures of elements ingested by such dying stars. There is no mainstream alternative explanation for this core physics. While the precise maximum size of a red giant can vary slightly based on its initial mass and metallicity, the fundamental process of expansion remains an absolute certainty. The physics governing how stars run out of fuel and restructure themselves is among the most thoroughly tested areas of our cosmic understanding. It's a bedrock principle. So, the standard stellar model clearly indicates that a star like Beidou should have created a death zone, extending out to at least one astronomical unit. Halla, however, orbits at half that distance. This naturally leads to a critical question. How do we know for sure that Beidou has already undergone this destructive phase and isn't merely on the verge of expanding?
That is the critical question. To know for sure that Beidou had already expanded, astronomers couldn't just trust a model. They needed undeniable proof from the star itself. And that proof comes not from looking at the star, but from listening to it. This is the field of astroseismology, the study of starquakes. Much like earthquakes reveal the inner structure of our planet, the surface of a star vibrates and oscillates based on what's happening deep inside its core. Different types of stars ring like different types of bells, each with a unique resonant frequency. To hear this stellar music, you need an exceptionally sensitive instrument. That instrument is NASA's Transiting Exoplanet Survey Satellite, or TESS. While designed to hunt for planets by spotting the dip in brightness as they pass in front of their stars, TESS's ability to measure stellar brightness with extreme precision makes it a perfect tool for listening to starquakes. For months, TESS monitored the light from Beidou. The data it sent back didn't show a flat, constant brightness. Instead, it revealed a subtle, rhythmic flicker, the telltale pulse of the star's vibrations.
This wasn't just noise, it was the star's heartbeat, encoded in light. And that pattern is a definitive fingerprint. The specific frequencies found in Beidou's light don't match the profile of a star that is still growing, burning hydrogen in a shell on its way to becoming a red giant. Instead, they are a perfect match for a more evolved, older star, a red clump giant. A red clump giant is a star that has already passed the tip of the red giant branch, its moment of maximum size. It has survived its most expansive phase and has now settled into a stable, long-term state of burning helium in its core. It's a star in its late middle age, not its volatile youth. This is the smoking gun. The star's own vibrations, read by TESS, confirm its history. Beidou has already lived through its red giant phase. The death zone where Halla is currently orbiting wasn't a future threat. It was a past event that the planet
somehow already survived. The evidence is in, and it leaves no room for doubt. The planet is in the star's former kill zone, and the star's own heartbeat confirms the danger has already passed. This one observation completely breaks the simple, standard picture of how planets and stars live and die together. So, if the old model fails, what takes its place? We've seen the planet, and we've diagnosed the star. Now, let's put them together. Our standard model for how stars evolve is a pillar of modern astrophysics, tested against thousands of examples. For a star of Bakdu's mass, that model makes a very specific prediction about its past. It calculates that at its peak, during the red giant phase, Bakdu would have expanded to a radius of approximately 150 million kilometers. That's one astronomical unit, the same distance that separates the Earth from our own sun. The star's surface would have reached this far out. But the observational data for Halla is just as clear. Using the radial velocity method, astronomers have pinned down its orbit with high confidence. The planet circles Bakdu at a distance of only 75 million kilometers, or about half an astronomical unit. And this is the moment where our straightforward picture completely breaks down. The orbit of the planet is half the size of the star's former radius. Halla is not near the edge. It is deep inside the volume that Bakdu must have once occupied. According to the model, it should have been engulfed. A gas giant orbiting within the tenuous outer atmosphere of a red giant experiences powerful drag forces. It would have lost orbital energy, spiraling inward to be vaporized by the intense heat. There should be nothing left. This isn't a small discrepancy. It's like finding a pristine ice sculpture in the middle of a furnace. The environment and the object are fundamentally incompatible. Even if we allow for uncertainties in the stellar model, the orbit is still comfortably inside the engulfment zone. So the measurements of Halla's orbit and Bakdu's current state are solid. The conflict between them is real. Science cannot simply ignore such a stark paradox. When a trusted model fails this spectacularly against hard evidence, it means our understanding is incomplete. The existence of Halla demands a new explanation. This forces scientists to consider two competing theories, each with profound implications. Either the planet somehow survived a catastrophe that should have obliterated it, or it's not a survivor at all, but a newborn with a very different origin story. So we have a planet that shouldn't exist, orbiting a star that should have destroyed it. The paradox is clear. Faced with this cosmic contradiction, astronomers are now evaluating two very different stories for how Halla came to be. The first possibility is that Halla is a survivor. In this scenario, the planet was always there, and when its star Bakdu swelled into a red giant, it was engulfed. To withstand this, models suggest Halla would need to be exceptionally massive, a true super Jupiter. But survival isn't just about heat. The bigger problem is drag. Moving through the star's atmosphere, even a thin one, would create a powerful drag force on the planet. This should have caused its orbit to decay rapidly, sending it spiraling into the star's core in a cosmic blink. How it could have avoided this fate is the primary weakness of the survivor theory. This leads to the second, more dramatic possibility. Halla is a newborn. This theory proposes that Bakdu wasn't always a single star. Instead, it was once a binary system, two smaller stars orbiting each other. This is where the story gets really interesting. In this scenario, the two stars spiraled inward and merged violently. This event would have ejected a vast cloud of gas and dust. From this newly formed debris disk, a second-generation planet, Halla, could have formed long after the stellar drama had concluded. The merger explains why the star never grew large enough to engulf the planet's current orbit. However, this newborn theory has its own puzzle. When two stars merge, the resulting single star is usually spun up to a very high rotational speed, like a figure skater pulling in their arms. But Becdu is rotating quite slowly. Explaining how the star could have put the brakes on after such a chaotic merger is a significant challenge for this model. So we have two compelling yet imperfect explanations: a survivor that defies orbital mechanics, or a newborn born from a merger that defies our understanding of stellar rotation. This isn't a sign of confusion. It's a sign of a healthy scientific process. Multiple testable hypotheses are now on the table, which is exactly what scientists want when faced with a true anomaly. This duel between two possible pasts presents a clear question.
Is there any lingering evidence, any faint signature left behind by one of these events that could allow us to declare a winner? To find out, we need to look closer at the more favored of the two ideas: the binary merger. To find out, we need to look closer at the more favored of the two ideas: the binary merger. This explanation for Halla's impossible orbit proposes a dramatic past for its star, Becdu. Instead of a single star evolving peacefully, scientists suggest Becdu was once part of a close binary system, fundamentally changing its life cycle. This scenario elegantly sidesteps the paradox of planetary engulfment altogether. It posits that Halla is not an ancient survivor, but a newly formed planet, born from a cosmic reset. In such a binary, one star eventually begins to expand into a red giant, as expected, but its proximity to a companion star changes everything. Its outer layers can extend to engulf its companion, creating a common envelope phase, where both stars orbit within a shared atmosphere. This intense gravitational interaction and friction within the shared gas causes them to lose orbital energy rapidly. This dramatically alters their individual evolutionary paths, leading towards an inevitable collision and merger. This violent process doesn't just create a single, short pause, new star. It also expels a substantial amount of gas and dust into space, forming a massive, rotating debris cloud around the freshly fused star. This ejected material, rich in heavy elements, provides the perfect environment for a second-generation protoplanetary disk. Within this disk, new planets can form relatively quickly. Planet formation models indicate this process can occur on timescales as short as 1 to 10 million years, a blink of an eye in cosmic terms, making it plausible for Halla to have formed post-merger. While directly observing such a merger is rare, other post-merger systems exist. These systems often display unusual chemical signatures or orbital configurations consistent with a violent origin. The binary merger theory offers a natural explanation for both Becdu's current state and Halla's seemingly impossible location, replacing the problem of survival with a new, equally dramatic origin story. However, it's critical to note that there is currently no direct smoking gun evidence specifically confirming a binary merger event at Becdu itself. This explanation, while compelling, remains an inference. It is attractive primarily because it solves the paradox so neatly, but it remains a powerful model, not a confirmed observation for this specific system. So, if the binary merger scenario provides such an elegant solution, what prevents scientists from declaring it the definitive answer? What specific evidence do we still need to move from compelling hypothesis to confirmed reality?
And what observation could finally settle this cosmic debate for good?
Before we hunt for a definitive answer to how Halla survived, it's crucial to pause. The duel between the survivor and newborn theories is exciting, but the speculation rests on a bedrock of new, undeniable truth. So let's strip away the hypotheses for a moment and focus on what the Bechdel system has proven for certain right now. First, the planet Halla is real. Decades of radial velocity measurements confirm it. A world with at least 1.5 times the mass of Jupiter is locked in a 93-day orbit. It's there. This isn't a model or a simulation. It is an observed object in our galaxy. Second, the star Bechdel is old. Its starquakes, measured through astroseismology, prove it has already lived through its red giant phase and is now a much smaller core helium-burning star. It's not a young star yet to swell. It is a stellar veteran that has already completed its most destructive expansion. When you put those two facts together, you reach a third, inescapable conclusion. The established facts are clear. The simple, textbook model of how a single star evolves and interacts with its planets is incomplete. The story we thought we knew has a glaring exception, and its name is Halla. This isn't a failure of science, it's the engine of science. An anomaly like this is a gift. It tells us exactly where our knowledge is thinnest and points a giant arrow toward new discoveries. The Bechdel-Halla system isn't just a puzzle, it's a signpost, telling astronomers that planets can exist in places previously written off as cosmic graveyards. Regardless of whether Halla is a survivor or a newborn, its existence single-handedly proves that planetary systems can persist or be reborn after their star's red giant phase. This fundamentally expands our understanding of where and when to search for other worlds. The hunt for exoplanets just got a lot more interesting. So we are left with a solid foundation of fact and two compelling competing narratives. On one side, a planet that somehow endured a fiery cataclysm. On the other, a planet born from the ashes of a violent stellar merger. Both stories fit the known evidence. But science isn't satisfied with a story. It demands proof. This brings us back to the central question for the astronomers working on this puzzle. With two plausible pathways, is there a single decisive test that could distinguish between the survivor and newborn scenarios? Is there a smoking gun waiting to be found that could finally settle this cosmic debate for good? From a puzzling observation, through the laws of stellar life and death, we've arrived at the frontier. The duel between a survivor planet and a newborn planet leaves us with one clear path forward. To solve this mystery, astronomers can't just look at the planet. They need to read the chemical history written in the light of its star, Bechdel. We end where all good science does, with a clear question and a plan to answer it. The next decisive observation won't come from discovering another planet or measuring its orbit again. Instead, the key is hidden in the very composition of Bechdell's atmosphere, waiting to be unlocked by a technique that acts like a cosmic chemistry test. This test requires pointing some of Earth's most powerful telescopes, like those at the Keck Observatory or the Very Large Telescope, at the star. Their goal is to perform high-resolution spectroscopy, splitting Bechdell's light into a rainbow of incredible detail. Within this spectrum, astronomers will hunt for the fingerprints of specific elements. This search isn't for just any element. The primary target is lithium. In a normal single star like Bechdel, Lithium is steadily destroyed in its core over billions of years. By the time it has become a helium-burning star, it should have very little lithium left. But if Bectu was formed from the merger of two other stars, the story changes. A stellar merger is a violent, churning event. It can dredge up fresh material or create new elements, leaving the resulting single star with a unique chemical signature. In this case, models predict that a post-merger star could show a surprising abundance of lithium, an amount completely inconsistent with its apparent age. Finding that lithium would be the smoking gun. A positive detection would provide powerful evidence for the binary merger, strongly suggesting that Halla is indeed a second-generation planet born from the chaos. If, however, Bectu's atmosphere has a perfectly normal, lithium-depleted composition for a star of its age, it would weaken the merger theory. It wouldn't prove the survivor scenario, but it would make that unlikely path more plausible. This is how science moves forward. It's not about having all the answers at once.
It's about finding the single, decisive question that can be answered with the tools we have now. The existence of Halla has given astronomers a new and urgent puzzle, forcing them to refine the rules we thought we knew about the fate of planets and the aftermath of a star's life. The telescopes are watching. The data is coming. And the answer to how a world can cheat death and be reborn from the ashes of a star is waiting to be found. Not in speculation, but in the faint photons of light that have traveled across the galaxy to bring us Bectu's story.